Hi and welcome to the first video. I'm going to assume you know nothing about Fortran. So first of all, we need to install the compiler. So sudo pacman in a terminal -s gcc-fortran. That's going to ask me for my password, and after that we'll have everything installed. So let's check the version, gfortran version --version. And I have 15.2 GCC Fortran, so gfortran, and I'm going to open up a new text file with neovim, say test.f90. It is a simple demonstration. The F90 indicates that we're going to be using the freeform Fortran. This allows for longer lines, line continuations, comments are different. Freeform Fortran has the exclamation mark to denote a comment, so this is a comment. And let's brighten up the highlight so you can see that properly. So this is a comment in Fortran. You can insert this in freeform Fortran anywhere else, really anywhere you want. And everything after the exclamation mark is a comment. The program in Fortran then begins with program, the name of the program, say test, and let's add the closing program, so end program. Every Fortran structure, once you open it, you have to close it. The name at the end is optional, but it is highly encouraged. Also, Fortran is case insensitive, so no matter how you write the end program, or you can even skip the spacing altogether in between the end and program, it is still going to be able to interpret the end of the program. This is very common in Fortran. Spaces do not really matter at all. Indentation doesn't matter. It is a matter of taste. So there are 5 basic intrinsic types of variables. We have integer, real, complex, logical, and character types. Let's go and have a few examples. So as you can see, I already declared a couple variables, but I missed the most important part, especially in Modern Fortran, which is the implicit none statement at the beginning. This is going to indicate to the compiler that we're not going to have any implicit conventions, say for instance I and j, as well as l, k, m, and n, and any other variables starting with those letters were considered to be integers in previous compilers and previous standards of Fortran. Many bugs occurred because of that. So the program simply breaks down into implicit none, the variables, and any executable statements below for now. As I said, we have integer, real, complex, logical, and character types. So let's go ahead, give some values, and print out some statements with the aid of the print function. This is going to print into the screen, which is denoted by the print part. The asterisk denotes that is going to come out in any format the compiler believes is the most accurate. The comma is to separate the executable statement with the arguments we're going to hand in. So yeah, let's do that. Now that that's done, let's write and quit. I'm quitting only to demonstrate clearly how to compile with gfortran. So gfortran, the name of the file. If we execute this as is, we're going to get an a.out file, as you can see, which is executable. I'm going to remove this one. So remove a.out, and let's compile it with an output name, so -o, and let's say test.x to indicate it's going to be executable. Now we have the test here, and we can run it as text. This is actually better to see in neovim, so let's go back there and execute it from here. Alright, so as you can see now, we get I equals to 0, even though we did not declare explicitly I. This is simply because we have allocated the memory, or at least the compiler has done so, and that memory just so happens to have had the value 0 for the integer. This can cause a lot of issues, especially with real values, which have not been assigned, but the variables have been declared, and the memory thus allocated. We do get a 1 for j, which is correct. You can see that we get a 1.5 both for x and for y with the same number of digits after the decimal place. So this is actually telling us that the default precision for our compiler is double precision. For Y, I did explicitly say this with D0, which is the Fortran way. I'll be talking about that in a short while. For Z, I simply set it to 1, but it is a complex number, so the imaginary part must be 0, which is what we're getting. The boolean is false, denoted by the dot false dot, and the string is only T. This is because we did not specify the length. So let's see what attributes we can define for each variable type. For the integer, we can actually have, according to older Fortran notation, times 4, or times 8, or times 16 to indicate the precision for the integers. For more modern compilers, we could have it here, so 4, 8, 16. However, this is not portable. My compiler in particular uses 1, 2, 3, and 4 to indicate the precisions. So the more appropriate way is to actually here use one of the two following options. We can use a library which is intrinsic, and it is called the ISO Fortran env for environment. By using this sentence over here, we're explicitly saying that we're going to use all the precisions that the ISO Fortran environment gives. So here we can just use int for the integer 8 or 16 or 32 or 64. So I'm going to be explicit here and give it a 16, int 16. For the real, we have the same issue, the same older conventions, the same portability conditions, as well as for the complex numbers, and I'm going to give it a real 64. Here it actually starts with 16, so you see 8 is not allowed. For complex, we have basically the same. So what is the other option? We can actually here define an integer. So integer, and let's use the keyword parameter. This indicates we're not going to be changing this integer. It is going to be constant throughout the program, and if we try to actually modify it, it's going to break the compilation. So let's say real precision, and we're going to use an intrinsic function, so selected real kind. This is going to give us a precision for a real kind, and for this we need the number of digits we want and the range in which we're going to be working. So let's say 10 here. This would indicate a 10 to the 10 minus 1 range. We can actually use 6, so it would be 10 to the 6, so a million minus 1, and from minus a million plus 1, that's going to be the range we're going to be dealing with the real numbers. And we can also use the same for integers, so say int precision selected int kind in this case. And here we do not have the decimal places, so we are only going to be selecting the range. 6 for the same as the real kind, yeah. And here we can just use our new defined precisions. For the logical, there is a similar way to use selected logical kind, and for the character as well. This allows the machine to store more efficiently the values, especially for logical types, but I'm not going to go into much detail on that. What I'm going to say is that for the logical, you can either have a true, like this, or a false, like this. Both are between dots, and this is the standard for all logical operations. Finally, for the character, what was missing before is that we actually have to have a length attribute here. So len for length equals, say, 20. That should be enough to get the whole phrase. And it is similar to the precision. We need to specify how many characters we're going to have in our string. We did not print anything. So let's go back and print everything again. Let's execute from here. Alright, so I is still 0, we did not modify that, and j is still 1. Should not affect the precision, because we're only going to be writing zeros and 1. Any precision for integer is going to be able to deal with that. For x and y, we're having a bit more zeros, quite a few more zeros actually, than 16. We have 20 places after the decimal point, if I'm not mistaken. And this is because even though we did select 16 decimal places, the minimum precision that satisfies this condition and also the range we're interested in is the quadruple precision. So this is what the machine chose for the precision of x and y. As for z, it is the same. We did not change that, as well as the logical. And notice that now the string is complete. As you can see, the strings are written between either one set of single quotes or one set of double quotes. If we want a double quote inside a string, we're going to use a single quote to wrap the entire string. And if we want the other case around, we're going to use double quotes. A very interesting fact in Fortran is that we can actually select a substring. This is fairly common, though not usually taught. And say we want to isolate the 4 first letters, so we would have to use a parenthesis from the first index. Fortran is by default 1 indexed, though you can actually change that, and to the 4th inclusive item, so that's going to be the word this. We can actually save this and compile. I do not have the command here, so gfortran, and the name of the file, I put the executable. Now let's run it. As you can see, I have indeed isolated this from the entire string. If we want to only get one index, we just have to say for the s, we would only write 4 to 4. We do not write a single 4. We have to say started at 4 and ended at 4. As a last note, we can also have arrays. We can turn every single of these data types into arrays, or rather have arrays from these data types by including the sentence dimension, the keyword dimension, when declaring the data types and specifying the dimension. So for instance, dimension 3 would create I and j as arrays of 3 elements each. It is only the default, so if we say have a parenthesis after I and say 5, then I is going to be an array of dimension 5, so with 5 elements. This can be extended, so if we want, say, an array of 5 by 5, we would have to use a comma and use another 5. By default, all these arrays are going to be one index, so it's going to be from I 1 through 5 in the first argument and 1 through 5 in the second one. So if we want to go from, say, 0, because some people are going to go from 0 coming from Python or places, we can simply do this from 0 colon to 4. This is going to be an index, first index 0, last index 4, and we have the same dimensionality. We can also set this in the dimension part. So let's say 0 through 3, and it's going to give a 4-dimensional array for the j integer. The rest are considered scalars if not specified, which is different from a 1-dimensional array. It is worth noting, if you try to compile something like that, assigning a scalar to a 1-dimensional array is going to throw an exception. As a last note, we can actually construct these arrays in a couple ways. So the simplest one would be, for instance, I equals, we're going to be using square brackets. Older notation uses this, parenthesis with slashes inside to denote the construction of an array. So Modern Fortran uses square brackets. It's going to be, for instance, 1, 2, 5, and 8, and 9, because we defined a 5-dimensional array. First item, 1, is going to be for index 0. The last one, 9, is going to be for index 4. This is an explicit way of defining arrays. So for the second way, we're going to be using an implicit do. For this one, we're going to be using I equals brackets again, and using the parentheses. Before I forget, actually this I is supposed to be a double indexed array. So here we actually should delete all of this. Sorry, I meant this. All right, now it is a one-dimensional array. Inside brackets, we're going to say calculate the squared values from 1 through 5. So that would be n times n. Since we have not declared n, we should do that right now, integer n. We do not care about the precision. We're going to be going from 1 through 5. It's going to be more than enough. So n equals 1 as the first value in the loop we're going to be using up to 5. And let's print this too and see what happens. Alright, as you can see, the first array was constructed explicitly and the second array was constructed indeed with the square of the values from 1 through 5. Going back, we can actually have the last way here, though I'm not going to go into much detail yet, but you can construct the array explicitly index by index, so element by element, by using this parenthesis. We're going to be using, say, the element 1, setting it to 1 to replicate this first array. Then the second one would be I2 equals 2, the I3 equals 5, I4, and so on. So you get the idea. This obviously is very tedious to do by hand, but it is very useful to do so in loops, which we'll be going to do in a couple of videos. And as a last note before I forget, we can actually define the precision of integer, real, complex numbers with an underscore. So for instance, x equals, say, instead of 1.5, which we had above, we can use 2.5 underscore and the precision we have selected for that real number, which is real PR. We can do the same for integers. So for instance, j item 1, element 1 would be set to 1 underscore int PR for the integer precision we have selected. This is very important. It avoids many truncation errors and rounding errors. Fortran does allow for us to, say, use x equals 2.5, but in the implicit conversion we are actually transforming from a simple precision to a quadruple precision, which we have chosen at the beginning, and that can definitely and often does come with a lot of rounding error. So I do encourage you to be as explicit with your numbers as possible. With integers, there's not all that much problem unless you go out of range, but with real numbers and complex numbers, it is very, very important. You may notice that for y, I have chosen D0. That's from an older standard in which, say, 1 point is simple precision as well as 1 point E0. 1 point D0 is for double precision and the Q for quadruple, but some compilers do not support it, some machines do not support this. So to be most modern, you should use either the intrinsic ISO Fortran environment library or the selected real kind, integer kind, logic kind, and character kind for each precision. Yes, I did forget to actually record this part. It is very important, but I forgot it. That's why it's so different. So that's it for this video. Next video I'm going to be going over a couple simple operations, mathematical operations which are intrinsic in Fortran, logical operations, and the concatenation operation to join strings in Fortran. I hope you've enjoyed it and you could take something out of it.